purpose of this video is to cover two topics. The first is this idea of conjugate priors. Sometimes I'll use the terminology of conjugate pairs. And the second is to look at the fact that the posterior distribution is going to be a balance between the amount of data and the strength or precision of the prior. So we'll begin with this concept of conjugate priors or conjugate pairs. And there's Bayes' theorem. And two really important parts are the likelihood function, shown right there, and the prior. Now, if we think about the likelihood function is really determined by the data. Now, if you think of what we typically do, probably shouldn't do, but we often collect the data and then do some analysis. Actually, we would be better off if we were to say, okay, what is the underlying ecological or environmental process? What sort of a likelihood would reflect that process? Then collect data that is consistent with the likelihood function, that meets all the assumptions, and do the analysis. But in any event, there's a very strong linkage between the likelihood and the data. So here what we have is a whole list of likelihood functions. And in this column, we have conjugate pairs, the corresponding conjugate pairs. So as long as the likelihood function, one of these folks, is a member of the exponential family, it's known as the exponential family, then all these guys are members of the exponential family, so they're going to have conjugate priors that are also members of the exponential family, and that's going to make calculation of the posterior distribution extremely simple. So for the first 6 weeks of this seminar, we're dealing with binary dependent variables. When we've got binary dependent variables, the appropriate likelihood is going to be the binomial, and it will have as its conjugate prior a beta distribution that will allow very rapid and exact calculation of the posterior. And the magical formula, and it kind of looks like magic, but the magic is all explained in the appendix, works something like this. If we've got a binary dependent variable, binomial likelihood, with y successes in n trials, and if we specify our prior as a beta, so we're going to have prior as a beta, and the beta is conjugate to the binomial likelihood. If we have a beta distribution and we give it parameters a and b, then we can automatically, instantly, and exactly calculate the posterior distribution. It's going to be a beta a star b star, where a star is equal to y plus a, and b star is equal to n minus y plus b. So let's go through an example. What I'm interested in is the proportion of the people who are right-handed, and I can represent that as theta. And defined in this way, theta is also going to be the probability that a randomly selected person will be right-handed. So what I know is that if I collect my data on handedness in a way that's consistent with the binomial distribution, that's going to be easy enough to do, then I can specify my prior as a beta, and then I'm very easily going to be able to calculate the posterior. So I'll need to begin with, I know I'm going to need a beta distribution, but what are my A and B parameters going to be? And there's a couple ways I can arrive at my A and B parameters. On E-class, you've got beta prior generator.R program, and just by trial and error, you can put in different A and B parameters until you get a beta distribution that reflects what seems a reasonable prior belief about what proportion of the people in the population are right-handed. But there's another way to do business that rather explicitly relies on prior knowledge that I have. So if I consider my family, my mother, my father, my brother, my sister, my wife, myself, there are 4 right hand and 2 left hand. And what's explained in Kruschke's text is that if I have this as prior knowledge, then that prior knowledge can be captured in a beta 4-2, 4-2 distribution. So I'm going to try that. That's what a beta 4-2 distribution looks like. And it sort of reflects a reasonable sense of my prior knowledge of the proportion of people that would be right-handed. The problem, however, anytime you use one of these distributions as a prior, it's never going to be exactly what you'd like to see. So, for example, if I look at my beta 4-2 prior, you can see that there are non-zero probabilities that the proportion of the population that is right-handed might actually be less than 0.5. I know that's impossible. So this is not a perfect reflection of my beliefs, but it's a good starting point. So I'm going to choose this as my prior. And then what I'm going to do is collect my data, and I need to collect that in a way that is consistent with the binomial distribution. So I'm going to get Y successes in N trials. And the main thing about these N trials is that they're independent and that theta remains constant throughout. And that's really not going to be a problem because that's what will happen if I just randomly select N people and determine their handedness. Let's say I do this. I get Y is equal to 9 out of 10 people that are sampled. And then I just use the formula beta A star B star. A star equals Y plus A equals 9 plus 4 equals 13. And B star equals N minus Y plus B, which gives me 10 minus 9 plus 2 equals 3. And there we go. There was my prior distribution, a beta 4-2, and my posterior distribution immediately, accurately, well, maybe not accurately given my prior, but very quickly calculated as a beta 13-3. So that's how we can use conjugate priors to a known likelihood function to speed up calculation of the posterior. Now what I want to do is go over the idea that the posterior is a blend between the amount of data on the one hand and the strength of the prior on the other hand. So in this figure, we've got increasingly large amounts of data as we move in this direction. So here we've got 1 success in 5 trials, 4 successes in 20 trials, 20 successes in 100 trials. In every one of these cases, the proportion of successes is equal to 0.2. As we go down, we have increasingly stronger priors. A beta 1-1, a beta 15-15, and a beta 120-120. Because the mean of a beta distribution is A over A plus B, then the mean of all these priors is going to be the same. It's going to be 0.5. So we've got kind of a contradiction between the data suggesting that the probability of success is 0.2 and the prior, which is centered on 0.5. The posterior is going to be a blend between the amount of data and the strength of the prior. So if we begin with this first row, a beta 1-1, we have a flat prior. And so the priors are shown by these dashed lines. And we see we've got flat priors that say that in terms of our prior belief, there's an equal probability that the value of theta is 0, anywhere between 0 and 1. Between 0 and 1, we have this constant value for the probability of success. In the case where we've got a flat prior, the data are permitted to speak for themselves. So the posterior is shown by the solid line. The posterior becomes increasingly stronger peaked with more and more data. So the posterior with a flat prior is determined entirely by the data. In the second row, what we have is a moderately strong prior. Now, these dotted lines here, here, and here, these reflect the mean values of 0.5, and you can see that these dashed priors are centered on 0.5. But with increasingly large amounts of data, you can see stronger shifts from the prior to the posterior. And then in the bottom row, we have a very strong prior, a beta 120, 120. So if we look at the shape of these priors, we can see that we're pretty darn certain in our prior that the value of theta is very close to 0.5. When we've got very little data with a prior that is this strong, our posterior is going to be essentially the same as the prior. With increasingly large amounts of data, we're going to get bigger shifts, but with a prior that is this strong, even with a large amount of data, even with n is equal to 100, we're not going to get very much of a shift. So, in conclusion, this video, two ideas. One, the idea of conjugacy, and the second idea that the posterior is going to be a balance between the amount of data and the strength of the prior.